Hello, my brilliant college algebra friends. I decided to make a video for my discussion this week. So I thought that we could approach this from a classical model using the 5 common topics of invention. Mathematics isn't always approached this way, but I think that it can make a fundamental difference in the way that we understand it. So, first, we are asked to explain how to determine graphically whether a zero of a polynomial is a multiple zero. So let's define a zero. What is a zero? Well, a zero is sometimes called a root, and it is going to cross the x-axis at some point, right? So this is a root or a zero of a number. Basically, where f of x equals 0. So the input value of a function is going to produce a 0 output. This is basically saying when y equals 0, then what is our input value? So here, we can see that this mark, if we use 1, 2, 3, 4, and scale by 1 on our x-axis, then our 0 is 4. Our root is 4. Okay, so let's draw a function on this graph. But wait, this graph isn't labeled. And that's a naughty thing. We cannot draw our functions on a graph that do not have a defined scale. So let's do that. We have a y and an x, and let's just go in increments of 1, simple scale. Now you know you don't always have to label every single tick mark on your axis, but you should represent both the positive and the negative scales on your axis. All right, so now that our scale is discernible, we can now draw a function. So I would like to get some specific points here that I was thinking about. There and there. And let's do, you know what? I think I want to scale my y-axis a little differently because it doesn't always have to be the same as the x-axis. I'm going to do these in increments of 2, so this will be negative 4, and this will be negative 8, and this will be 4, and this will be 8. So let me plot this point, and I'm going to attempt to draw a function here, hitting specific points that I had in mind. I did it. Brilliant. Okay. Well, it's not beautiful, but it is what it is. So, what do we have on our x-axis? We have here a 2 and a negative 2. So what does that mean? Well, it means that our x-intercepts are at 2 and 0 and negative 2 and 0. Now, they are also our real zeros. Now, a real zero is just in opposition to a imaginary zero, which is something that I guess we'll get into later. But so these are our real zeros because they actually hit the x-axis at these 2 points. So if a real zero of f of x is k, as we're told in our chapter 4, then let's call x-intercept 2 k. Let's do that, and we'll just call it k. It doesn't matter. So now if I were to say that f of x is x minus k, then I can go ahead and translate this particular intercept and say that we must be talking about x minus 2. And it's a 0 because if I were to set it equal to 0 and solve for x, then I would get x equals 2, wouldn't I? And that is what we have here. Okay, so we have x minus 2. And because we have this, we know that it has to be one of our factors of this polynomial. We can call this one x plus 2. And that helps us understand that the factors that are involved in this particular polynomial that I drew. Now let's compare these two zeros of the function. How are they alike? So they're both x-intercepts. They are points on a continuous function, right? You wouldn't have to lift up your pen to draw this line. And they both have multiplicity. If you can think of some other way that they are alike, you can leave it in the comment. How are they different? They are different in that one is positive and one is negative. One crosses the axis when the other one does not. This does not cross the x-axis. And because of that, they have different multiplicities. And if you can think of another way how they are different, you can leave that in the comment as well. Now that we have a new term, multiplicity, what is multiplicity? Well, basically it's how many times a particular number is a 0. So for this given polynomial, how many times does this particular number become a 0? In other words, this factors out to x minus 2. And we want to know, in a fully factored form, does this polynomial have 2 x minus 2's? Or does it have 2x plus 2's? Or are they singular? Because if they had 2, then we'd have to write a little exponent outside the parentheses there. Now there is a way to figure this out. When we used comparison on the 2 points, we said that they both have multiplicity and that these 2 points have a different multiplicity. When our goal is to write this function in a completely factored form, we need to know its multiplicity. It's very important to have the right function, to graph the right function, or to represent the right function symbolically. So let's look at the relationship between the behavior of the graph at the x intervals and its multiplicity. This particular 0 at 2, x equals 2, corresponds to, as we said, this particular factor. Because this line right here, never crosses the x-axis, it has an even multiplicity. So it could be 2, it could be 4, it could be 6. Wow, that's a lot. So this particular line does cross right at x equals -2. Now, because it crosses, it has to have an odd multiplicity. So it could just be the singular 1, or it could be 3, or 5. You know your odd numbers. We found our zeros. We have how many turning points? Well, there's a turning point, and there's a turning point. So let's say we have 2 turning points. So what does that tell us? It tells us that we have a degree 3 polynomial, which will also be the exponent on our leading term. If we were to FOIL in our factored polynomial. So it tells us something else. It means that we should have 3 factors. So what we have right now are only these 2. And we don't see anything else that crosses or touches the x-intercept. So that tells us that one of these is going to have a higher degree than 1, because we need it to equal the 3 of the 3-degree polynomial. So we said that one of these zeros has a multiplicity that is even. Can you remember which one it was? Right. It's the one that does not cross the x-axis. So it is this one. It does not cross the x-axis. So this particular factor needs to have an even degree. Now, because we know that we have a degree 3, the number of factors has to equal 3. We have 1 here. We don't have to put a 1. But then if we know this has to be even, 2 is our only logical choice. And so this function factors out like so. Now the circumstances with which this becomes important is when we need to factor out our polynomials. It's a very thorough way to do it. It's convenient, and we can thank the fact that the factor theorem states that a polynomial f of x has a factor of x minus k only if f of k equals 0. And we know that f of k, or let's say f of 2, does indeed equal 0. All right. Well, that's excellent. I hope that this video helped you understand. If you FOIL out this entire thing here, you should get, let's see, I think it's x to the third because it is a third degree, minus 2x squared minus 4x plus 8. Yes, plus 8. And if you notice, well, I moved it, but if I move it back, remember that that 8 is our y-intercept. All right, so we can take all of that and feed it to our hungry little maybe it's our Pac-Man. Yeah, it's our Pac-Man. You ever notice that Pac-Man is like a cannibal? He's this circle that keeps eating other circles. And he is deathly afraid of Negative parabolas. That's all it is. All right, have a great day.